Good evening.
Good evening, sir.
You have just finished with the previous lecture, na? Mishra ma'am.
Yes, sir.
Okay, okay. कितने होते हैं मतलब अभी अटेंडीज कितने होते हैं जनरली आपके इसमें?
Sir, it keeps on changing.
कितने माया? सॉरी,
सर चेंज होता रहता है, कभी होते हैं 35 40।
कभी होते हैं। ओके ओके।
Generally 25.
24 25 होते हैं ना? आई अंडरस्टैंड। ठीक है। And moreover, this is the last lecture. You already had 3 lectures previously. तो 2 हो गए और अब ये तीसरा है, so I understand थोड़ा तो you must be feeling tired, that too in vacation. ठीक है। Oh, I'm sorry, I lost my connection. I'll just share my screen now. Am I audible?
Yes, sir.
Okay. So we have finished with Unit 1 and we move on to Unit 2, that is on chromatographic techniques. Now, in this, you will be introduced to the fundamentals of chromatography, and you will be given some idea about different types of classifications based on which uh, several chromatographic techniques can be classified. Further understanding how separation occurs in chromatography and what is the efficiency of separation. What can be called as an efficient separation in chromatographic techniques. Further down, we have few techniques based on planar configuration and few others in column configurations like TLC, which is a planar chromatographic technique, and those which are done in uh, column configuration like ion exchange or HPLC or ion chromatography, etc. See, in this syllabus, uh, in this revised syllabus, what you will find is we have introduced HPLC, which was not there previously this year, and ion chromatography. These are the two additions to the previous syllabus which we used to study. The intention was to have some idea about separating cations, which are generally done with ion exchange chromatography, and anions by ion chromatography. These two are two different techniques, ion exchange chromatography and ion chromatography. One is used mainly for cations exchange, which is ion exchange, and anion exchange is with ion chromatography. And then we have a superior technique called high performance liquid chromatography. And we have removed counter current chromatography from semester 2, which is now taken up in semester 3. So these are the things which we intend to study in chromatographic techniques. I assume you already have some idea about chromatographic techniques. So can anybody tell me what all you have studied or you know about chromatography, which is one of the most important separation technique. Basically, it is a separation technique. Separation techniques play a vital role in any kind of analysis, chemical analysis, or in analytical chemistry specifically. Separation techniques are, they are mandatory, because what happens is all samples which we come across in any form, solid, liquid, or a gas, contains several components, and we need to find out the number of components in any sample, of course. But before we come to know the number of components, we need to separate them first to exactly have an idea about the number of components. And for that, we generally do any separation technique. Prior to separation, we always do sample preparation. For that, we studied several sample preparation approaches in the previous unit. About 60 to 70% of the sample preparation techniques were taught to you. There are few others which would be taken up in subsequent semesters. So the whole status of chromatography under separation science is immense. And there are certain guiding principles of chromatography which one should know to understand what actually one can achieve, one can do with several chromatographic techniques which are available now. The whole story started around 75 years back. But the basic principle, guiding principles in chromatography is that in such separations, there are two phases. One is a stationary phase and the other phase which moves. If both the phases start to move, it will not be considered or termed as a chromatographic technique. We saw two phases in liquid-liquid extraction, in Craig's countercurrent extraction. So they were extraction techniques. Because both the phases started to move. When you shake, they move. But in chromatography, the principle is that one should remain stationary and the other should move. And if this condition is met, then that entire process is known as chromatography. Now, if you look at the types of stationary phases available, when we look at the forms of samples available in nature, we find substances to be present as solids, liquids, or gases. For a phase to be stationary, it is understood that it cannot be a gas. So therefore, there are three forms of stationary phases. So stationary phase can be a solid. It cannot be purely liquid. So if you want to still use liquid as a stationary phase, that liquid should be coated on a solid support. That a liquid can be coated on a solid support. Or the third form of stationary phase is a gel, which is again a kind of a solid, but it has pores of definite size. So when we work with chromatography, when we say that there are stationary phases and there are moving phases, and it caters to varieties of samples in any form, the stationary phase available with us is in three forms: solid, liquid coated on a solid support. When it is coated on a solid support, the solid does not take part in separation. It simply holds the liquid. on its surface. And then we have the gel. Now, when we talk about stationary phase as such, stationary phase, when we say it is solid, these solids are converted into small particles. The basic material of stationary phase is silica, SiO2. This is one of the most widely explored stationary phase materials, solid stationary phase material. There are others as well, like alumina, Al2O3. But then there are other limitations associated with those kind of materials. Silica is widely used, it is widely available, relatively inexpensive. But the problem with silica is that it is highly polar. That is what we understood last time. Silica is highly polar. So people naturally would do some modifications on it so as to make it more stable. It should not be very reactive. When we say stationary phase, which is silica, which is bare silica, that means unmodified silica. Now this silica is made in the form of small particles. How to put this stationary phase or use this stationary phase? It should be in the form of very small particles. Particles of size in the region of micrometer range. The most common size of particles used in chromatography is 5 micrometers. In most of the columns of the stationary phase which you will see, which are in practical use, you will find that the particle size is 5 microns or 5 micrometers. And these small particles are packed in a chromatography column. These columns have their own dimensions. When I say dimensions, means it can be of a certain length. It would have, a certain internal diameter. The most, commonly used columns containing silica particles have internal diameter of about half a centimeter. You know what is 1 centimeter? Half of that would be the internal diameter of these chromatography columns, which contains these small silica particles, generally of the size of 5 micrometers. Size can vary. It can go down to 1.7 micrometers as well. It can be of 3 micrometers as well. There are different particle sizes available in different chromatographic columns. So these stationary phase are tightly packed in a column of specific dimension, specific length, specific internal diameter. These columns are generally made up of alloy, which can withstand high pressure as well, which are inert to, of course, silica and the samples which are injected, which pass through these columns. So that is how, I mean, these are certain things which we consider under principles of chromatography. Looking at the mobile phase, which moves, which has to move. So we know gas could be a potential candidate for that. Liquid also moves. So liquid can also be a potential candidate for as a moving phase, as the mobile phase. And the third kind of a phase, which we call as a supercritical fluid. The first two, gas and liquid, are natural forms. Natural forms. Supercritical fluid is not a natural form. It has to be created. It has to be generated. Supercritical fluid. This supercritical fluid is generated at a definite pressure and temperature with certain substances. Substances like CO2, ammonia, even water. So at a definite temperature and pressure, these substances get converted into a form which we say as supercritical form. The properties of supercritical fluid as such is between the gas and the liquid. They are not as mobile as gas, less than gas, but more than liquid. Viscosity in between gas and liquid. Diffusion coefficients, again in between gas and liquid. So basically, supercritical fluid is something which acts as a bridge between a gas and a liquid in terms of a moving phase. So thereby we have three different kinds of moving phases in chromatography: gas, liquid and supercritical fluid. The columns जो मैंने अभी बात किया, columns are either packed columns. Packed columns means these small stationary phase particles are packed inside the column of a particular dimension, and those are known as packed columns. And then there are other which are known as open tubular columns. Open tubular columns, which are also known as capillary columns. If I talk about the length of columns, this length can vary from 0.05 meters to 100 meters. The lengths of the column which are used in different chromatographic techniques can vary from as small as 0.05 meters, which is 5 centimeters, to 100 meters. You know how much would be 100 meters? That is the length of the columns. So there are two kinds of columns. One is packed column and the other is open tubular columns or capillary columns. The difference is open tubular columns are very narrow bore columns. The internal diameter of common packed columns, as I said, is around half a centimeter, around 4.7 mm. And open tubular columns, they are about 4 to 5 micrometers. You can understand what would be the, what is micrometers, what is centimeter, millimeters and micrometers. So micrometer is the internal diameter of open tubular columns, which are also called as capillary columns. And in such columns, it is difficult to pack them with stationary phase particles. So what happens next? In such columns, the stationary phase is coated on the inner walls of the capillary columns or the open tubular columns. So there is no particles which are packed into such columns, but because the internal diameter is so less, it is difficult to have small particles of stationary phase. So it is coated with a layer of these stationary phase material in the inner walls of those capillary columns. That is how it functions. That is how the columns are, and that is how they are classified as packed columns or open tubular columns. And we know that these columns or these techniques with such versatile columns, they find use in, of course, chemistry, biochemistry, biology, pharmaceuticals, quality control, in forensics, in environmental samples, in agrochemicals, in petrochemicals, in research, of course. So there are many areas where chromatography plays a significant role in separating samples, constituents in a sample. And as I said, they have two phases, stationary phase and the moving phase. Now you know the types of stationary phase and the moving phase. You also have some idea about the types of columns which are being used in these chromatographic techniques. And what is the status of the stationary phase in these two types of columns? Now, this figure gives us an idea about what actually happens in a chromatography, any chromatographic technique. Once you inject your sample into a column, of course they are going to come out. The analytes which are getting separated would come out, and this would be seen first by the detector, and then detector gives you an output, and the output is something like this. This is a detector response versus time plot in any chromatography. Detector response or signal is on the vertical axis, and on the horizontal axis you have time or volume. Time or volume. Detector response can be, or detector signal can be in any unit. Unit could be volts, millivolts, counts per second, counts per minute, so on and so forth. The horizontal axis could be, as I said, with respect to time or with respect to volume. Volume would be in ml and time would be in seconds or minutes. It will not be in hours. It will be second or minutes. And this is what we get. We get these peaks. All chromatographic techniques generate these peaks. And these peaks correspond to the analytes separated in a given sample. This is a simple example where you can see that there are three peaks which are well separated from one another, which is known as baseline separation. That means this is your baseline, this is your baseline. So they are baseline separated. That means they are well separated from one another, and it is known as baseline separation because it comes down, it touches the baseline, and then it goes up. So all the three analytes in the given sample are baseline separated. That is all you need to know as of now. We'll come back to this slide again, but this is what is the output, and this figure is known as a typical chromatogram from any chromatographic technique. This is from a gas chromatography. Don't worry about what is gas chromatography, but it is a chromatogram which you will find in any chromatographic technique. Fine. We'll come to these terms, what these terms signify very soon, what this TM and TR and TR dash etc. signify, and many other things which are relevant when we understand principles. Now, if we look at, before moving ahead, I have made few slides which give us an idea about the common terms which we use in chromatography. The first term with which we should be conversant is eluent. Any liquid, any fluid which enters the column is called eluent, E-L-U-E-N-T. Any liquid. And that liquid which comes out from the other side of the column, other end of the column, of course, it would be the moving phase along with the analytes. That is known as the eluate. जो बाहर निकलता है उसे कहते हैं eluate, और जो कॉलम में एंटर करता है उसको हम कहते हैं eluent. And this process of entering from one side of the column and coming out from the other side of the column, this entire process is known as elution. This is known as elution. And chromatogram, which we just saw, a chromatogram is a graph showing the detector response as a function of elution, time or volume of analytes. जो हमने अभी एक फिगर देखा. Any chromatogram from any chromatographic technique will give us the detector response on the vertical axis with respect to elution time of your analyte. कितने समय में निकलता है वो, या कितने वॉल्यूम लेके निकलता है of analytes. So that is a chromatogram. The next important thing is linear flow rate. See, flow rate we know. कितनी फ्लो रेट है, कितना लिक्विड कितने समय में जाता है कहीं भी, that is known as the flow rate. Now, flow rate in chromatography is defined in two ways. One is linear flow rate and the other is volume flow rate. One is linear flow rate and the other is volume flow rate. Now, why there is this subdivision in flow rate? There has to be a meaning to it. Now, this meaning, I mean the way in which we further divide flow rate, this is dependent upon the length of the column. See, as I said, that the length of the column can vary from 0.05 meters to 100 meters. Therefore, when you have very long columns, we define distance. We use the term distance. And when we have short columns, we work with volumes. That means we have linear flow rate, which is defined as the distance which is traveled by the solvent through the length of the column in a unit time. that is linear flow rate. Distance, when we talk about distance, we cannot say 5 centimeter is a distance. Like when we talk about 10 meters, then we classify it is as some distance. So linear flow rate is applicable to when we work with very long columns. Very long columns we work with in GC, but very short columns in the range of say 5 centimeters to 30 centimeters, we work with HPLC in HPLC. So linear flow rate is defined as the distance traveled by the solvent, which is the mobile phase, through the length of the column per unit time. कितना समय लेता है मूविंग फेज पूरे कॉलम के अंदर से ट्रैवल करने के लिए, कितना डिस्टेंस कवर करता है per unit time. That is linear flow rate. And the second is volume flow rate. It is defined as the volume of solvent or the moving phase traveling through the length of the column per unit time. एक होता है समय और एक होता है वॉल्यूम. तो एक कितना वॉल्यूम ट्रैवल करता है थ्रू द लेंथ ऑफ द कॉलम इन यूनिट टाइम ऑफ द मूविंग फेज. एक होता है समय और कितना वॉल्यूम. ये दोनों चीज, कितना डिस्टेंस ट्रेवल करता है कितने टाइम में, या कितना वॉल्यूम निकलता है एक डेफिनेट टाइम में. सो फ्लो रेट इज डिवाइडेड इनटू टू, linear flow rate and volume flow rate. Volume of solvent that travels through the length of the column per unit time. उसके बाद आता है very important aspect, that is dead time, which is denoted by Tm. What is dead time? See, dead time has a is a very significant term, because retention time, which is a characteristic of a particular analyte, depends upon dead time. In chromatography, we always work with retention times, and retention time for a particular analyte depends upon the dead time. और जितनी भी चीजें क्रोमेटोग्राफी में होती हैं, जितने टर्म्स भी यूज होते हैं, they all are dependent on retention time, right? All features would directly or indirectly are related with retention time, but retention time is related to the dead time, and dead time is the time taken by the unretained mobile phase to pass through the column. अब ये जो मोबाइल फेज होता है, it should be in chromatography, it should not react with the stationary phase. This is important. ये बहुत इंपॉर्टेंट है कि उसको रिएक्ट नहीं करना चाहिए स्टेशनरी फेज के साथ. दिस इज अ प्रीरिक्विजिट. अब ये होता है कि जब कोई लिक्विड जो मोबाइल फेज होता है, वो जब कॉलम में एंटर करता है और जब बाहर निकलता है जिस भी फ्लो रेट से, तो नेचुरली कुछ समय तो लेता होगा. समय किस पे डिपेंड करेगा? कितना लंबा कॉलम है, द लेंथ ऑफ द कॉलम. So it would change. This time which it takes to pass from one end of the column to the other end of the column would change, and the time which is taken by the solvent, which is unretained, while passing through the column, is known as dead time. जब एनालाइट को मोबाइल फेज ले जाता है कॉलम में से, तब वो कैसे ले जाएगा? अपने से तेज तो ले नहीं जा सकता, बट इट विल इटसेल्फ टेक सम टाइम टू पास थ्रू द कॉलम. तो सबसे पहले ये निकाल लिया जाता है कि जो मूविंग फेज है वो कितना समय लेता है कॉलम में से पास होने के लिए. तभी तो हम एक्चुअल रिटेंशन टाइम किसी एनालाइट का निकाल पाएंगे. And that time is dependent on several factors. Length of the column, type of the column, even composition of the moving face, because mobile face तो एक तो चीज होती नहीं. There can be 2-3 components in a mobile face. Injection volume, जितना volume inject करते हैं, it depends upon that. So that time holds a significant place in chromatography, because retention time of analyte is directly related to the dead time, and dead time is dependent upon, again, type of column, composition of the mobile phase, length of the column, injection volume, so on and so forth. Then is the retention time, which we all want to know in any chromatographic technique. TLC में आप जानते हो, आपने निकाला है RF वैल्यू, रिटेंशन फैक्टर या रिटार्डेशन फैक्टर. तो यहाँ पे उसका समय को कहा जाता है रिटेंशन टाइम. फॉर ईच कंपोनेंट, द टाइम नीडेड आफ्टर इंजेक्शन of the mixture onto the column until that component reaches the detector and gives a peak. That time, जब हमने सैंपल को इंजेक्ट किया और जब हमने वो पीक मैक्सिमा देखा डिटेक्टर में, उतने समय को हम कहते हैं रिटेंशन टाइम, जिसको हम कहते हैं TR. अगर रिटेंशन टाइम है तो रिटेंशन वॉल्यूम भी होगा, बिकॉज हॉरिजॉन्टल एक्सिस पे हमने बताया था इट कुड बी आइदर टाइम और इट कुड बी वॉल्यूम. सो रिटेंशन वॉल्यूम of the mobile phase, the volume of the mobile phase required to elute a particular component or a solute or analyte from the column. कितना वॉल्यूम हमको लगता है मोबाइल फेज का कि हम एक कंपोनेंट को एक कॉलम में से बाहर निकाल दें. दैट वॉल्यूम इज नोन एज रिटेंशन वॉल्यूम, एंड दैट कैन बी कैलकुलेटेड बाय knowing the retention time and the flow rate and the volume flow rate. दोनों को अगर हम मल्टीप्लाई कर दें, this is time, say for example in minutes, this is flow rate, so it will be ml per minute. So minute cancels, so you'll get volume. So this is the volume of the mobile phase which is required to elute a particular component from the column. I hope things are clear. Hello?
Yes, sir.
आप लोग, are you there?
Yes, sir.
Okay.
Sir.
Now moving ahead, we have few other things, other terms. The other term is known as adjusted retention time, which we call as TR dash. Now here what you can see here is, it is the difference between the retention time of the analyte, that is TR, minus TM. TM is the time taken by the mobile phase only to move from the one end of the column to the other end of the column. This difference is known as the adjusted retention time or the true retention time of the analyte. और यही चीज हम इस फिगर में देखते हैं. Again, this is what is shown here. What is shown? This is analyte 1, analyte 2, analyte 3. What is this? This is methane. This is the carrier gas. This is the moving phase. Moving phase कितना समय लेता है? TM. यहाँ से इंजेक्शन हुआ, एनालाइट का। तो यहाँ से इसका पीक मैक्सिमा जब हमको मिला डिटेक्टर में, कितना समय लगा? TM, दिस इज दैट टाइम। और यहीं से हमने सैंपल भी इंजेक्ट किया था। तो सैंपल ने कितना टाइम लिया? से फॉर एग्जांपल दिस पीक, सेंटर ऑफ द पीक, तो इसको हम क्या कहते हैं? TR, फ्रॉम दिस पॉइंट टू दिस पॉइंट, दैट इज रिटेंशन टाइम जो हमने देखा। एडजस्टेड रिटेंशन टाइम और द ट्रू रिटेंशन टाइम इज TR dash, which is equal to TR minus TM to give TR dash. And this is what is you can see here in this equation. TR dash is equal to TR minus TM. So so now you can see that how retention time is related to the dead time, and without which, and we work with TR dash, and for any chromatographic analysis one should have the idea about TM, which needs to be calculated, which needs to be found out for a particular experiment, because it changes with so many things, with type of columns, with flow rate, with the length of the column, so on and so forth, injection volume, etc. So this needs to be defined to calculate TR dash, which is the true retention or the adjusted retention time. The other thing that is, which is also important, is relative retention. Relative retention, when we talk about two components. See, chromatography is used only when you have two or more than two components. If there is only one component, chromatography is of no use, because then you don't need any separation. But if there are two or more than two components, then and only then you use chromatography. Now, what is relative retention? For any two components, the relative retention is the ratio of their adjusted retention times. That means it gives you the ratio of the two retention times, adjusted retention times, to give you a value, a constant value. Greater the relative retention, greater is the separation between the two components. हमको क्या चाहिए? Separation चाहिए, ज़्यादा separation चाहिए. So alpha value, which is relative retention, is more, greater the relative retention, greater is the separation between the two components. And relative retention now becomes independent of flow rate, because you have taken a ratio. When you have taken a ratio, naturally relative retention will be independent of flow rate. जितना effect इसको पड़ेगा TR2 को, उतना ही असर TR1 को पड़ेगा flow rate का. So relative retention becomes independent of flow rate. अभी हमने देखा था moving phase में ये TM is dependent upon so many factors. But the moment you take a ratio of the adjusted retention times, it becomes independent of flow rate. And it is expressed as TR2 upon TR1, where TR2 is generally taken to be the one which is greater value as compared to TR1. And therefore it is taken in the numerator and the smaller value in the denominator, so that alpha will always be greater than 1. That is what is the whole crux of relative retention. That means when there are two analytes, you want to find out how they move in relation to each other under the given conditions, under the similar conditions, how they move. And that relative behavior can be estimated through relative retention, and that is calculated through this expression. And one of the last but not the least term which is used in chromatography is capacity factor. Now here, what if you could see here, this is represented as K dash, capacity factor or retention factor, and this is one of the most important factors which one needs to evaluate when you find out or when you report anything. report any method or when you optimize any method, you need to calculate capacity factor. It is a measure to monitor the performance of the column. See, we always compare the performance of the different columns which are available to us, and to measure that, to monitor that, we find out capacity factor. The longer a component is retained on the column, greater is the capacity factor K dash. जितना वो समय अंदर ज्यादा रहेगा उतना कैपेसिटी फैक्टर ज्यादा हो जाएगा. And that is simply, you know, this is adjusted retention time, TR minus TM, divided by the dead time. What you get is capacity factor or retention factor. So greater the value for the two components, greater would be the performance of the column. अब ये होगा कि कितना greater, कितना ज्यादा हो. See, chromatography basically is a relative technique. It is not an absolute technique. Relative technique से मतलब है कि आपके पास कोई सैंपल है जिसमें 3-4 कंपोनेंट्स हैं, तो आपका क्वेरी ये है कि मुझे ये बता दीजिए इसमें कौन कौन से कंपोनेंट्स हैं. कितने हैं वो तो है, लेकिन कौन कौन से हैं, नाम क्या है. Chromatography cannot find out the names, honestly. Chromatography cannot help you in that until and unless you have reference standards for those components. Reference standards for those components. Now, with the advancement in instrumentation, you have a library of compounds whose retention times under optimum chromatographic conditions are there available in the library, in the computer library, where you can check a particular kind of a particular substance. You can match with the existing one in the literature, but of course you need to do that same experiment under the same conditions. If your conditions vary, you cannot compare. So basically it is a relative technique. It doesn't give you absolute values. आपके पास उसका स्टैंडर्ड होना चाहिए, तभी आप बता पाओगे कि ये पीक इस कंपाउंड का नाम है. अदरवाइज आपको सिर्फ पीक दिखेंगी, आप ये नहीं बता सकते ये पीक का मतलब क्या है, इसका मतलब क्या है, इसमें क्या चीज है. That you cannot do. So it is a relative technique. और दूसरी इंपॉर्टेंट चीज एक और भी है कि जैसे हम मॉनिटर करते हैं परफॉर्मेंस ऑफ अ कॉलम, और जैसे आपका एक टेंडेंसी होता है कि जब आप कुछ काम करते हो, आपको कोई क्रोमेटोग्राफिक सेपरेशन के लिए एक्सपेरिमेंट दिया है, तो आपने कोई कॉलम रखा, कोई मोबाइल फेज रखा, कुछ फ्लो रेट रखा, और आपने 3 या 4 कंपोनेंट को सेपरेट कर दिया, बेस लाइन सेपरेशन कर दिया. लेकिन आपका कुछ रिटेंशन टाइम आया होगा, चारों कंपाउंड्स के रिटेंशन टाइम्स होंगे. यही काम मैंने किसी और को दिया, उसने भी क्या किया, कोई अपना कॉलम लेके, कोई अपना रिटेंशन टाइम, अपना मोबाइल फेज लेके चारों को बेसलाइन सेपरेट कर दिया, उसका भी चारों का सेपरेशन हो गया. तीसरे जने को दिया वही सैंपल, उसने भी अपने हिसाब से अपने कॉलम कर दिए. अब आप ये पूछोगे कि सर कौन सा सही है, कौन सा गलत है, कौन जना ने सही किया, कौन जना ने गलत किया. अब क्रोमेटोग्राफी ये बोलती है तीनों ने सही किया. अब तुम बोलोगे एक चीज के 3 सब लोग सही कर रहे हैं. यस, यू आर सेटिस्फाइंग द मिनिमम कंडीशंस कि बेसलाइन सेपरेशन होना चाहिए, और तीनों ने बेसलाइन सेपरेशन कर दिया है. सो ऑल आर राइट. बट ये चीज जरूर होगी अंदर कि कोई ज्यादा सही है, कोई थोड़ा कम सही है, बट ऑल 3 आर करेक्ट. अब ये ज्यादा सही और कम सही का मीनिंग ये है, इफिशिएंसी में मिलता है इसका आंसर. किसका सेपरेशन कम से कम समय में ज्यादा से ज्यादा एनालाइट को बेसलाइन सेपरेशन जिसने किया है, उसको हम कहेंगे कि ही इज मोर एफिशिएंट. all three are correct, but the one which has separated all four components within the shortest possible time is more efficient. किसी का पूरा टाइम लगा होगा 5 मिनट, उसने चारों सेपरेट कर दिए. किसी का टाइम लगा 7 मिनट, उसने भी चारों सेपरेट कर दिए. किसी का लगा होगा 10 मिनट, उसने भी चारों सेपरेट कर दिए. तो क्रोमेटोग्राफी वाइज इट इज फाइन, परफॉर्मेंस इज फाइन, बट इफिशिएंसी, सबसे ज्यादा इफिशिएंसी उसकी होगी जिसने 5 मिनट में 4 सेपरेट कर दिए, उसके बाद होगी जिसने 7 मिनट में 4 सेपरेट कर दिए, और उसके बाद होगी जिसने 10 मिनट में 4 सेपरेट कर दिए. कल को अगर किसी ने 4 मिनट में वो 4 सेपरेट कर दिए तो वो ज्यादा एफिशिएंट हो जाएगा. तो क्रोमेटोग्राफी, दो चीजों पे मुझे एम्फसाइज करना है कि क्रोमेटोग्राफी इज अ रिलेटिव टेक्निक, इट्स नॉट एन एब्सोल्यूट टेक्निक. You cannot come to know the name of the component just through chromatography, through the peaks in the chromatogram. You need to compare it with a standard which is run in the same identical conditions, so that you can match your retention times, so that dead time does not change. Because dead time is a very critical thing. It can change with column, with flow rate, with injection volume, etc., etc. And secondly, the efficiency of separation in chromatography has to be such that it fulfills all the criteria of chromatography. It separates, baseline separates all the analytes, but within shortest possible time, which will give you a more efficient chromatography. इसीलिए chromatography में कहा जाता है कि optimum chromatography, ऑप्टिमम, बेस्ट तो होता ही नहीं कुछ भी. देयर इज नथिंग लाइक बेस्ट इन क्रोमेटोग्राफी, बिकॉज आज आपने कुछ अच्छा काम किया, लेकिन कल इसको किसी और ने इससे अच्छा कर दिया तो आप बेस्ट नहीं रहे, वो हो गया. एंड किसी और ने उसको 2 मिनट में कर दिया वही काम को, तो उस दिन वो ऑप्टिमम हो गया. किसी ने उसी को 1 मिनट में कर दिया तो वो ज्यादा ऑप्टिमम हो गया. सो दैट इज हाउ things move in chromatography. It is not absolute. हाँ, सही सब हैं, लेकिन efficient सब नहीं है. कोई कम है, कोई ज्यादा है. तो ये कुछ चीजें थी. Have you understood this much? हेलो रिचा, खुशबू.
Yes.
Okay.
Yes, sir.
Yes.
Okay, मतलब have you followed this?
Yes.
हाँ, આ ખબર પડે છે તમને ખુશબુ?
Yes, sir.
ઓકે, તમે તો આ બધું વાંચીને તો આયા છો. I mean sorry, વાંચીને मतलब कि you have already studied in BSc,
Yes, sir.
isn't it?
Yes, sir.
तो उसमें भी ऐसे ही होता था ना, यही सब पढ़े थे ना कि कुछ और पढ़ लिया था. मतलब ऐसा तो कोई ऐसा डिफरेंस तो नहीं लग रहा ना?
No, sir.
Very good. See, chromatography, it doesn't change. Only the way in which we express or we teach, that might be different, but the things remain the same. And that is how, what I feel is, one should look at chromatography to have a better understanding of, because most important thing in chromatography, of course, once you have optimized the method, second is interpretation. Without interpretation, I mean, it has no value, because all chromatograms look the same. All chromatograms look the same, but one needs to interpret from these terms which is more efficient, which column gives you a good performance, and which is the most optimum chromatographic conditions. These are the things which one needs to look into when we use any chromatographic technique. जितनी भी chromatographic techniques आपने पढ़ी हैं, जानी हैं, उसको जानने के लिए ये चीजें. बस एक लास्ट स्लाइड में बता रहा हूँ, उसके बाद then I'll stop. One more slide just. With this understanding about the principles of chromatography and some very important terms which are used in chromatography. क्योंकि इतनी सारी chromatographic techniques हैं, तो it is always better to classify them so that understanding becomes easier. तो जितनी भी chromatographic techniques हैं, उसको 4 तरीके से classify किया जा सकता है. There are 4 different ways in which different chromatographic techniques can be classified. एक है type of stationary phase, कैसा होता है, solid होता है, liquid होता है, या even gel होता है. और moving phase जो liquid होता है, gas होता है, supercritical fluid होता है. That means combination, suitable combination of stationary phase and mobile phase. जैसे solid and liquid, or solid and gas, and solid and supercritical fluid. So you have 3 such combinations. फिर liquid and gas, फिर liquid and liquid, and liquid and supercritical fluid. So you have 3 more combinations. So classifications based on the type of stationary phase and the classification based on the type of the mobile phase. And of course, classification based on the configuration. Configuration मतलब 2 ही तरीके से क्रोमेटोग्राफी की जाती है, या तो कॉलम्स में की जाती है या फिर प्लानर कॉन्फ़िगरेशन, जैसे पेपर क्रोमेटोग्राफी और टीएलसी एक प्लेन में किया जाता है, और कॉलम में बाकी सारी टेक्निक्स, दुनिया की जितनी भी क्रोमेटोग्राफिक टेक्निक्स हैं, वो सारी प्लानर होती है. कुछ टेक्निक्स हैं जैसे सेपरेशन टेक्निक, जैसे इलेक्ट्रोफोरेसिस, जेल इलेक्ट्रोफोरेसिस, वो प्लेनर कॉन्फ़िगरेशन में होती है. बट व्हेन यू टॉक अबाउट क्रोमेटोग्राफिक टेक्निक्स, only chromatographic technique, not electrophoresis, then there are only 2 techniques in planar configuration, that is paper chromatography and thin layer chromatography. Rest all the chromatographic techniques are done in column chromatography. And the 4th type of criteria to classify chromatographic techniques is based on mechanism of retention. कौन सा ऐसा मैकेनिज्म है जिसके बेसिस पे हम डिफरेंट क्रोमेटोग्राफिक टेक्निक्स को क्लासिफाई कर सकते हैं. सो दैट इज वेयर आई स्टॉप टुडे, एंड देन वी विल अंडरस्टैंड स्टेप बाय स्टेप द क्लासिफिकेशन, the mechanisms on which several chromatographic techniques are based, and then we will move on to certain more important fundamentals, theoretical aspects, fundamental aspects, which are actually will have meaning in the practical aspects. Those important terms we'll be doing, and once we have done through with that, then we will move on to the actual techniques and their own specific principles. So thank you everyone for your presence today. Still there are 20. I'm happy that at least you all are coming and attending these lectures. So if you have any questions, you are most welcome. कोई ना कोई सवाल छे तो पूछो. કોઈ સવાલ નથી. 5 વાગી ગયા છે તો હવે તો સવાલ નથી. ઓકે, ठीक है, तो फिर आई स्टॉप हियर.
यस सर.
ओके, चलो, मैंने जब बोला कि स्टॉप करता हूँ तो किसी ने बोला कम से कम. ओके, so thank you once again. Take care, stay safe. God bless.
Thank you, sir.
Thank you, sir. Bye.
Bye. we'll meet on Wednesday at 10 a.m.